Okay. Hello everyone. From past 2-3 classes, we are discussing on numericals on Carl Pearson's correlation coefficient. In our last class, we have been discussed in detail these four numericals, this one and this one, then this one and this one. In detail we have been discussed and I instructed in that video that in which way you have to maintain your note, okay, because in the book it has been given directly uh, at many places, but in that video I instructed in which way you have to maintain your note. In today class we are going to discuss another type of numerical in which we have bivariate frequency distribution. So you just put this heading calculation of correlation coefficient for a bivariate frequency distribution. So here somewhat introduction part, just I am going to explain. May you can write your note, okay, or you can say this is the theoretical part, uh, which explains how we are going to be solved if we have bivariate frequency distribution. If two random variables are there, but it is in the form of frequency distribution, then how we are going to handle this type of numericals. Okay, so let's start. So carefully you have to watch in which way you have to maintain the note. Okay, so when the data are considerably large, they may be summarized by using a two-way table. This line you have to write here. For each variable a suitable number of classes are taken. Okay, here you have to put full stop, keeping in view the same consideration as in the univariate case. No need to write this line up to this much. You have to write up to this much only and put the full stop. Then if there are m classes for random variable x and n classes for y, that means random variable y, there will be in all m, here m cross n is there, m cross n, here it is written m small m cross or into n cells in the two-way table. How it is, I am going to be explained with the example. You just wait. First focus that what you have to write down in your note in for this introduction part. So by going through the pair of the values of x and y, we can find the frequency of each cell. The whole set of cell frequencies will then define a bivariate frequency distribution. Bivariate frequency distribution. The column totals and row totals will give us the marginal distributions. The column totals and row totals will give us the marginal distributions of x and y respectively. This is written as x and y, because here you can see that this introduction part is referring this table. Okay, you can see that along this the variation of x values, along this variation of y values, but this one is nothing but marginal marginal distribution of y. Okay, marginal distribution of y, that means gy. For particular value of y, x is changes along this way. Along this way, marginal distributions of x we can found. That means particular value of x, y value has been changed, or this gy is nothing but your, we can write this one is your fxy, summation over x. All the x value is going to be added up for corresponding y value. So marginal distribution of y. So along this way, you can say that along row marginal distribution of y, along column marginal distribution of x. So same thing it has been written. The column totals and row totals will give us marginal distribution of x and y. So here the column, along the column marginal distribution of x, along row marginal distribution of y. A particular column or row will be called as conditional distribution of y for given x, or of x for given y respectively, that we know. Suppose that bivariate data on x and y are presented in a two-way correlation table shown on page 10.13. Here for this book it is page 13, 10.13, but you have to write, suppose that the bivariate data on x and y are represented in a two-way correlation table. In bracket you just write figure 1 or table 1, you just write in bracket here correlation table 1, you just write two-way correlation table 1. Okay, the bracket in bracket shown in figure no need to write. So where there are n classes of y placed along uh, n classes of y placed along horizontal line, and m, here m is the small m classes of x along vertical lines, and fij is the frequency of individuals lying in ijth cell. Okay, what it is, here you can see that along you can say along horizontal we have x values, along vertical we have y values, but here by mistake it has been written that y placed along horizontal lines, n classes y placed along horizontal line, but in the table y placed in vertical line. So here you have to correct that, instead of horizontal here you have to write vertical. Okay, vertical. Similarly here m small m small m classes of x along vertical lines, but in the table it is along horizontal line. So here instead of vertical line you have to write horizontal line. Okay, horizontal line. This much you have to correct at the time of writing your note. So up to this much you have been written. Okay, now we are going to go for the mathematical representations of this table. This is the general uh, table, you can say, which represents n classes of y and m classes of x. And okay, and here you can see for each x and y value one cell or one, you can see this one cell we can found. Okay, one cell we can found. So each cell contains the corresponding frequency fij lying in the ijth cell. It is very much similar with your probability distribution table, bivariate or 2D random variables probability distribution table. So you just recall that this table already we have been discussed in our class. This is the table which represents the probability distribution of two random variables x and y. So these are the probabilities corresponding to two-dimensional random variables. So here along horizontal, here for this table along horizontal all the y values are represented, and along vertical all the x values. Okay, so this probability is represents a p11, right? P11, small p 11. This is your belongs to p 1 2, x is 1 2, and this is your marginal distribution of x, marginal distribution of x equal to 1. So this is your x equal to 1, so this is nothing but p of x equal to 1, where y varies from 1 2 3 4. You can see this one. Okay, y varies from 1 2 3 4. So these things already we discussed. So exactly similar table here, this one, but here instead of this one, here all the cell values represents the probability. Okay, all the cell values represents the probability, and here in this table y values taken along row and along horizontal, you can say, and x values taken as the vertical. But here in this table x values taken along horizontally and y value taken vertically. So not to be confused, just simple modification, but the approach, the process will be the same. But another difference you can found that in this table, probability distribution table, uh, for 2D case, each and every cell value represents the probability. But here each and every cell value, here x1 y1, x2 y2, xi yi, xm y1, sorry, this is xi y1, this point will be, or this cell belongs to xm y1. These points are belongs to frequency. Okay, these points are belongs to frequency. So here the small simple language has been modified. There these all the points belongs to probabilities, and here these are the frequency. Okay, so gy, this gy is nothing but your we can say marginal distribution of y, this gy, because that means for y1 x values 1 2 3 up to m we have to consider, or we can consider this one, f of summation over f of x, f of xy, all the x values has to be considered. So same thing, it has been written that sum of x, f of xy equal to nothing but equal to gy is the sum of the frequency along any row, and this is also in either language we can say that this is your marginal distribution of y, right? Likewise, sum of f xy for all values of y, this one will be represented as fx, small fx is the sum of the frequency along any column, any column. Also in either way we can say that this is called as your marginal distribution of, marginal distribution md, in short I written md, marginal distribution of x, right? And here we can observe one thing, that sum of x and y that means all the values, these all the entire values, the whole sum is nothing but your total number. Okay, total number. There all the in case of your probability distribution table, you just recall all the point value, if I am going to add, it will give the total probability, that will be 1, but here it will give you a total number. Okay, so here n is the total number, this will be nothing but summation over all the cell values, you can say. So sum of x, sum of y, so into sum of x, sum of y will be run over fxy, right? See here fxy is your pmf, probability, you can say that it is probability of mass function, probability mass function in case of distribution table, but here fxy is represent the frequency. Okay, this is the frequency, here fxy, only fxy is represent the frequency. But if we are going to consider, are going to compare with the distribution table, this fxy is nothing but called the PMF, probability mass function. Okay, as it is discrete values, so probability mass function. So now here sum of x, sum of y, fxy. This is the nothing but frequency. Fxy is nothing but frequency, density of frequency. You can say means for each cell frequency value. This is represents. If I will be add all the frequencies, that means summation over x, summation over y, fxy, or you can say summation over y, summation over x, fxy will be equal to summation over fxc. Each value here along all the columns we are going to get one fx here. This one along this one, this column will be fx1, this will be fx2, like this. Okay, so if I will add all the fx value over x, all the values of x, for see for this one will be fx1 and next one fx2. If I'll add fx sum of x, it will be give you the value n, or here you can found that this is your along row. You are going to get first row will be g y1, second will be g y2, like this. So sum of g y which runs over y, that means all the y values if I am going to consider, then also it will give you n value. Okay, or you just recall, if I will if this fx will be considered as the marginal distribution of x, and I will be consider all the marginal distribution of x. This will for the distribution table it will give you 1, and for the distribution table it will give you 1. Okay, but here it will give you total number of points or total number of observations. You can say total number of observations. So here we found capital N, and x mean obviously it will be 1 by n sum of x, sum of y, x into fxy, right? Or we can write summation over x into summation over y, fxy. So this is nothing but your fx, right? This is nothing but summation over fxy, summation over y, fxy is nothing but fx. That means we have to consider all the y values for a particular x value. That means you can say marginal distribution of x. Okay, so this fx is marginal distribution of all the x, right? This fx value is your summation over y, fxy. Now then if we are going to consider x into fx, which will run over x, this will give you the x mean, right? So x mean will be all the fx. See we can get fx1, fx2, or the marginal distributions fx3, like this. So fx1 into x1 plus fx2 into x2, fx3 into x3, fxn into xm. We have to add all the multiplications. X with fx divided by n will be give you the mean of x. Likewise, mean of y will be 1 by n summation over y into marginal distribution of y, that is your gy. Here sigma square represents the variance of x. So variance of x here we are going to calculate that 1 by n summation over x, summation over y, x square fxy. Okay, x square fxy. So see, for the mean it is your x fx. So obviously for variance it will be x square fxy minus mean of x square. Okay, you just recall the mean of random variables, how we are calculated. Sorry, variance of mean and variance of a random variable, discrete random variable. You just recall that if random variable x we have, the expectation of x is nothing but summation over x into pmf, right? pmf. Okay, so here and variance, that variance means expectation of x square. Expectation of x square will be summation over x square pmf, right? So likewise here sigma x square will be, sorry, here I told wrongly that if we are going to calculate expectation of x square will be this much, then variance of x is nothing but we know that ex square minus ex whole square. Okay, that things we know. So if we are going to consider this one, this can be written in this format also. This is your sigma square. Variance is nothing but sigma x square. Variance of x is also represented as sigma x square, will be expectation of x square minus expectation of x whole square, right? So here this is expectation of x square can be written as uh, x mean square, whatever written like here. Okay, and this is nothing but your summation over x and summation over y x square f of xy. Okay, see, if one random variable, single random variable, then this will be valid. But for if we have uh, random variables, they are connected with each other, two random variables, uh, or you can consider 2d random variable, 2d random variables, 2d random variables. Then for that, expectation of x will be nothing but, so it can be written as expectation of xy. In case of discrete, it will be summation over x, summation over y, x into y, then pmf into pmf, that we know. And if it will be continuous two-dimensional random variable, then it will be integration x y pdf, probability density function, into dx dy, that we know. Okay, so as in case of 2D random variable, expectation of xy for discrete will be this much and for continuous will be this much. So obviously, if we are going to consider variance of x in case of joint random variables, then it will be ex square. Ex square will be nothing but x square. This will be your what? For this will be, we can say, probability mass function for discrete random variable, probability mass function. Or we can say here in this case, this fxy is represents the common frequency for random variable x and y, common frequency. Okay, and here it has to be sum of x and sum of y, right? So here sigma x square will be calculated as 1 by n sigma x sigma y, summation over x summation over y x square fxy minus x mean square will be equal to 1 by n. Here summation over all the y fxy is nothing but fx, right? So x square fx sum of summation over x minus x mean square. Likewise, sigma y square will be y square 1 by n sum of y summation over y square gy minus y mean square. And the covariance will be how much? Covariance will be 1 by n summation over x summation over y xy fxy minus x mean, y mean. Okay, see, in general covariance we know that in general it is covariance of 1 by n xi yi minus x mean y mean. But if we have the frequency distribution, then for that, if we have frequency distribution, for that we have to multiply here as the frequency, corresponding frequency. So xy is the point, each and every point xy and corresponding frequency we have to write in this way whenever frequency distribution uh, data we have. So covariance xy will be 1 by n summation over x summation over y x y f xy minus x bar y bar. Okay, so this is all about this general table whatever we discussed. See, so here we have to stop our discussion. You just write down the note from here to up to here. Okay, pause the video and write down the note, and in our next class we are going to solve a question, this one using this concept whatever theoretical we discussed in this video. Here you can see that along horizontal x values are there, random variable x values are there, that is the age in year 18, 19, 20, 21. Along the y, sorry, along the vertical line or vertically, random variable y has the values, but in the classes 10 to 20 marks, 20 to 30 marks. So here you can see 10 to 20 mark, 18 ages students are 4, 50 to 60 marks, 21 ages of students are 4, like that. So this table explains or represents two random variables having the different frequencies. So for each x and y value one frequency is there, or you can say this is your bivariate frequency distribution table. So how we are going to find out the covariance, correlation coefficient for this, that we are going to discuss in our next class. Okay, so thank you so much for watching this video. Thank you.